Let's try to solve this non-homogeneous higher order equation using the variation parameters method, specifically the Wronskian of functions. So we need the previously prepared video for the Wronskian of an equivalent functions that is related to this item. And we are going to use this method because in the previously discussed method using a table of child particular solution for your y sub p, we don't have cosecant of 3x as our g of x. Okay? We only have sine and cosine for that. In short, we are going to specifically use another method so that we could actually come up with a solution of this. But of course, generally, the solution is still y sub c plus y sub p. So y sub c, we know that we are going to treat this g of x be equal to 0 to come up with the general solution intended for this homogeneous equation. And then, together with our y sub c, we can identify later the correct y sub 1 and y sub 2 coefficients, functions, needed for our y sub p in this method. But we still also need to solve for u sub 1 and u sub 2 taken from this. W here is the Wronskian, and again, a video discussing the Wronskian of equivalent functions will also be presented probably later or in the process as well. So let's start with y sub c here. So we will have for f of dy equal to 0, you will have d squared plus 9. That's d squared plus 9 times y equal to 0. So your auxiliary equation is m squared plus 9 equal to 0. Solving for the roots, m squared is equal to negative 9. So the m is plus minus the square root of negative 9. Obviously, we are expecting an imaginary solution because this is actually equal to plus minus square root of 9 times square root of negative 1, leaving us with the result m is equal to plus minus 3i. So with this form, plus minus bi, our a is 0, our b is a 3. We need this because the general solution for a homogeneous equation where the roots of the auxiliary equation are imaginary, expressed in this manner, e to the power of ax times c sub 1 cosine of bx plus c sub 2 sine of bx. Our a is 0, so 0x. So you have c sub 1 cosine of 3x plus c sub 2 sine of 3x. This is just equal to 1. So our y sub c is c sub 1 cosine of 3x plus c sub 2 sine of 3x. Pardon if my discussion is a little bit faster because we are assuming here that you were able to view already the process involved in solving y sub c and homogeneous equations. So with this now, this is already structured in this form. We can identify that this is our y sub 1 and this is our y sub 2, which will be integrated on this equation to solve for y sub p. We just need to look for u sub 1 and u sub 2 in the meantime. At the same time, the concept of Wronskian will involve these two functions. So we're going to solve the Wronskian of cosine of 3x and sine of 3x because it will be for our w. A concept will also be involved in w sub 1 and w sub 2 to solve for the prime to get the u's to be integrated here. Okay, so I am cautioning you that this discussion will be very long, but this would be worth a while. By the way, for the Wronskian of this was already presented in the previous video. Okay, I'm going to attach, or I am attaching below the link for solving the Wronskian of the specific item pertaining on the Wronskian of these two functions because this was already identified as equal to 3. The Wronskian of cosine 3x and sine 3x is equal to 3. It was actually generated from this. Cosine 3x, writing here two functions, and for the second row would be the first order derivatives of the first row. Sorry. So you will have here the first derivative of cosine is negative sine 3x times the derivative of the angle 3. I told you that the link is already provided below, but I'm just representing this because the derivation or the matrix form will also be used for w sub 1 and w sub 2. the derivative sign is cosine 3x, again for the angle times 3. So the correct matrix that we used before in solving for the Wronskian, which is 3, is cosine 3x, sine 3x, here negative 3, sine 3x, and positive 3, cosine 3x. Again, this was used to solve the Wronskian because the Wronskian is just equal to the determinant of this matrix. Showing this because we need that for W sub 1 and W sub 2 processes. Okay? Why do we need this? Because for U primes, you need the ratio of W sub 1 to W and W sub 2 to W. Now, how do we come up with the matrix to be used for our W sub 1? Here's the catch. For W sub 1, look into the first column of this matrix, make the first entry 0, and the last entry be equal to our original g of x here. Okay? If there are entries between, so all of the entries will be 0, just the last entry would be equal to our g of x. And our g of x presented in the original function, our equation rather, is the cosecant of 3x. So cosecant of 3x. Since it's just W sub 1, the second row will just be itself. Sine of 3x and 3 cosine of 3x. Okay? So for W sub 2, it's the second row that will be changing. And retaining this first row, cosine of 3x, negative 3, sine of 3x. So they are still both W, so still get the determinants of both. So when you look into this, that's 0. Then this diagonal, okay, minus that's cosecant. Cosecant 3x times sine of 3x. We know that cosecant of 3x is just 1 over sine of 3x. So times sine of 3x, cancel, you will have negative 1 for W sub 1. Okay? Take out of that. Next, here you will have this, okay, cosine. So you have cosine of 3x times cosecant of 3x, then minus this side is 0. So we know that our what do you call this one, cosecant is 1 over sine of the same angle. So you will have cosine over sine, which is cotangent of 3x. This is our W sub 2. This was our W sub 1 earlier. So we cannot take the ratio of W sub 1, this one here, I'm emphasizing to this entry, that's actually U prime sub 1. That's the ratio of W sub 1 and W. And U prime sub 2 is the ratio of W sub 2 and W. W sub 1 is negative 1 over our W, which is 3. So negative 1/3. That's the U prime of sub 1. Here, you will have cotangent 3x over 3. So you can rewrite this as 1/3 cotangent of 3x. These are now our U prime of sub 1 and U prime of sub 2. Okay, this time, let me move to the next page because I don't have much space here. Don't worry about the formulas because I have pasted here the formulas. Okay? Yeah, this one here. But let me remove this portion here because this is now our primes. Okay, U prime. Take note that our goal is this. We already have y sub c in the previous page. For y sub p, we need this. We already have our y's earlier. We need the u's, and the u's will be taken from this. So, here's the thing. For our u sub 1, it's the integral of u prime sub 1. And take note here, the dx will appear later. We're going to use x because it's x here. Don't be confused with why it is appearing because we are integrating and we can't integrate if we don't have dx. So our u prime sub 1 is negative 1/3, the integral of that, and I have here dx. Okay? So our u sub 2 is also the integral of u prime sub 2, and you will have here the integral of 1/3 cotangent 3x, and then you have here dx. Okay. Of course, you could have negative 1/3. The integral of dx is you have negative 1/3 x. Okay, that's for u sub 1. Take note, I am not adding c here, even if I'm integrating. This is just to continue with the process without appearance of c. Now, for this u sub 2, you can have 1/3 here, and then you have the cotangent of 3x dx. What do we need here? We actually have a certain process with the integral of cotangent, but since this is a 3, we need another 1/3, okay? Another 1/3 here to neutralize the 3 I'm adding to dx as our du. Okay, we cannot integrate this if we are not going to add here 3, because that's the concept of cotangent u du. Review, please take a review on that. In short, this will become 1/9, and the integral of cotangent 3x and then 3 dx. And the integral of that, you may review your formulas for integration. So you have here, that's actually the natural logarithm of sine of the same u, that's a 3x. Okay, so this is now our u sub 2. We have our u sub 1. Now let's look into the final solution for our y sub p, which is the integration of y sub 1 and y sub 2. Just for us not to be confused, going back to the previous page, our y sub 1 is cosine of 3x, and our sine of 3x is our y sub 2. Okay, so again, our y sub 1 is cosine of 3x, our y sub 2 is sine of 3x. And our y sub p, as indicated in this formula, is the product of u sub 1, y sub 1, plus u sub 2 and y sub 2. So u sub 1 is, again here, negative 1/3 x. So negative 1/3 x times cosine 3x. That's our y sub 1, again in the previous page. Then plus our u sub 2, which is 1/9 natural logarithm of sine 3x times our y sub 2, which is also another sine 3x. Take note, you can't multiply them because this is under a logarithm. Okay, so this is our y sub p. Now that we have this, we can now finally provide our final solution with y sub c plus y sub p. Let me copy the y sub c here. This is our y sub c. Okay, copy. Previous next page. I hope that I have some space here. Okay, let me just remove the other notations. Okay, this is our y sub c. Again, let me move this here. There's our y sub c here. Okay, so y sub c plus y sub p, finally our solution would be in this form. Y is equal to y sub c, c sub 1 cosine of 3x plus c sub 2 sine of 3x, and then your y sub p, which is minus 1/3 x. I forgot the x. 1/3 x, because you have here the x. 1/3 x cosine of 3x plus 1/9 of natural logarithm of sine 3x times sine 3x. You might want to place it there, but I could. That's okay with me. This is now the final solution of our given equation, and as mentioned, our given equation here may not be solved using the trial particular solution, the table presented in the previous video. So this is why we're using the Wronskian functions. Thank you very much for watching.